Thank you. When I was asked to do this talk, I really didn't have much idea of how it would fit or who would be listening and so forth. And I'm happy to say, quite by accident, that what I plan to say fits, albeit in sometimes curious ways, with the talks that have preceded it. Let me just highlight a couple of those things very quickly. One, Eric Davis's comment about how when you do advanced propulsion that's beyond the box or beyond what my colleagues in the physics department at CSU Fullerton would think of as normal everyday type physics, you do it very, very conservatively and discreetly and in small steps. The other thing that I would like to call attention to is that when you do this sort of thing, as York Dobbins has pointed out, you want to be sure that you're doing real physics, because it's easy to delude yourself into thinking that something might be serious physics and it turns out that it's not. So, my talk, I swiped the headline title from Stephen Hawking's recent thing on TV, Reaching Out to the Stars, because that's primarily what I want to talk about today. For the past 15 years, really, I've been doing the small steps, trying to keep it honest physics and all of that, but in the early days when I was figuring out what I thought might be going on, it was clear to me that there was more to it than simply small-scale thrusters that vibrate and do weird things and stuff like that. About a year ago, I was invited to John Kramer's 75th birthday symposium, and when I told John that I'd come, he suggested that I should give a talk, and I availed myself of the opportunity to start talking about what I'm going to spend probably more time on today than experimental stuff, but there is some experimental stuff, that is to say, reality does impinge on some of this a bit. Okay. Serious advanced propulsion in the modern world really starts with this guy here. It's a picture of Kip Thorne, Caltech, Feynman Professor of Theoretical Physics at Caltech for many years, now recently retired. This is from the time at which he did his epoch-making papers on wormholes, which you've heard discussed earlier today. That is to say around 1987 or 88. I'm not going to revisit the story of how he came to do that because of his buddy Carl Sagan. I am going to show you the abstract of his paper. Okay. He tried to present this as a pedagogical tool for teaching general relativity. Of course, nobody figured that was what he was really up to. Buried in an appendix to his paper is this. And this is the reason why Eric earlier this morning and others have commented that you need utterly idiotic amounts of negative rest mass material in order to do anything like so-called Alcubierre or warp drives or traversable wormholes. Indeed, that is what you need in order to produce what they call an absurdly benign wormhole. It turns out that you can use smaller amounts than a Jupiter mass of negative rest mass matter to produce a wormhole throat, but if it's less than a Jupiter mass for most interesting configurations, you're going to get throat flaring that screws up everything for miles around. Okay? So what you really need is on the order of a Jupiter mass of negative rest mass matter in, say, a sphere on the order of, say, 30 meters in diameter with a wall thickness on the order of maybe a meter or so, plus or minus a bit, and all that. And if you do the calculation, you find out that turns out to be much, much, much higher than nuclear densities of that sort of stuff. I'm going to show you the obligatory pictures that have been produced for this. This is the wormhole that Eric showed you a different version of. This actually, to my knowledge, first appeared in Morris in Misner, Thorne, and Wheeler's book on gravitation back in 1973, published in 73 by Freeman. And it was primarily at the instigation of Misner and Thorne's doctoral dissertation supervisor, John Wheeler, that it was included. This is the warp bubble hyperspace embedding diagram that you've seen. This is a recent rendition of a warp drive ship that's shown up on the web and so on. This is from one of Stephen Hawking's illustrated books, a spaceship in the act of producing negative rest mass matter in the ring and inducing in a wormhole throat through which it is about to proceed. This is from the 2002 Scientific American summer issue, I think, one of those. It's what is referred to in the trade now as a Stargate. What it is really short throat wormhole, okay, spherical in this case. One of the people who, I have a virtual group of folks who look over my shoulder and throw rocks from time to time and stuff like that. Nimbo Boldrini, if you were looking very carefully at Eric's slides, you would have found that he was one of the authors in one of the articles in the book that they edited. Okay, Nembo put this together for me about a month ago or so when I made some comment about infringing copyrights and that I was worried about that. Okay, in order to get the right perspective on this, it's always, no, actually, the real reason for this is the best Calvin and Hobbes cartoon I've ever seen. It's posted in my laboratory, okay? I'll do this without comment. Okay. Now, with that as preparation, you need to be sure to, serious skepticism is required in this business, okay? Okay, what does it take to do this? A Jupiter mass of negative rest mass matter, okay? That's really basically what you've got to do. And what I want to talk about today, I'll tell you a little bit about the experimental work that I've been doing later on, but what I want to talk about today is this, because what often passes for conversation about this misses a point which I think is important. And just to remind you how much a Jupiter mass of matter is, it's 2 times 10 to the 27th kilograms of stuff. That's 600 times the mass of the Earth or something. It's a very large amount of mass. Okay. Is there any chance that this can be done? And especially using only low, and by low I mean the best we can possibly produce. They are all low. Energy electromagnetic fields, because in this business electromagnetic fields are pretty much what you're limited to. Steam's the other option, and steam power isn't, obviously. No. Okay, where do you get a Jupiter mass of exotic matter? Okay, remember this has to be rest mass matter, stuff that you can stop in the laboratory, okay? Not stuff that's zipping along at the speed of light. I suppose you could contain it in something or something like that. But rest mass matter is the stuff that Morris and Thorne were talking about. The usual story, and when you see stuff on this topic on TV, what people usually talk about is by amplifying Planck scale wormholes. Presumably quantum gravity, which doesn't exist yet, the theory doesn't exist yet, nonetheless suggests that space-time foam at the Planck scale occurs and that there are wormholes flitting into and out of existence at that scale and so forth. And the idea here, and this was, by the way, proposed by Thorne himself in his early papers on this, is that somehow you get really super small quantum tweezers and grab one of these Planck scale wormholes and then you stretch it out and amplify it, whatever that means, up to macroscopic dimensions. Oops, wrong way. Okay, here we go. Next one. Another suggestion that's been made is that there may be naturally occurring exotic matter, cosmic strings, remnants from the initial creation of the universe and stuff like that, And that if you motor around in deep space and identify some of this stuff and put your tractor beam on it and drag it around and so on, you might be able to do that. Okay? By figuring out how to transform normal matter into exotic matter. This may sound to you like the least likely, but, and I must admit I didn't think it was very likely either. But I should point out, as Peter Maloney pointed out to me many years ago in a delightful conversation about all of this stuff, he said, you realize, of course, that in quantum electrodynamics, the bare masses of elementary particles are negative, and they're infinite. They have to be, because the renormalization program, in effect, adds a positive infinite energy that dresses it down to a finite value. Okay? That's this. Okay? The question is, how do you undress elementary particles? And in the standard view of the standard model of quantum mechanics, the answer to that is you don't. Okay, because the fluctuation process that produces the cloud of virtual photons and electron-positron pairs is not something that you can manipulate using low-energy electromagnetic fields. Okay. The question then arises, and the reason why Maloney and I were talking about this many years ago was because I was interested at the time in the question of how do gravity and inertia and all of this stuff interrelate, and what do elementary particles look like. It was obvious I wasn't going to invent quantum gravity. There are a lot smarter people than me who've spent lifetimes trying to do that and having not succeeded. So I went looking at general relativistic, semi-classical, and classical models of the electron, elementary particles. And it turns out there's a cottage industry in this. There are a bunch of people out there who at least used to sit around working out various models for elementary particles. There are some requirements that you're going to want if you're interested in gravity and inertia. It should include gravity, as gravity modification is something that will likely be involved. Okay? And it should be exact so that approximations don't cloud any issues. In other words, you want a theory that people aren't going to look at and say, oh, that's just an approximation, that's all just a lot of nonsense, if you can get it. Okay? The paper that set me off on the track that I'm going to tell you about briefly now was published around 1990 in the New York Academy of Sciences. It was a review article by Abe Ashtekar on his work on what he called new Hamiltonian variables for general relativity, his attempt at a quantum theory of gravity, which at the time, around 1990, was very fashionable. I was informed last fall at the Kramer Symposium by somebody who does this stuff that Ashtekar's view on this is no longer considered viable, which may or may not be the case. What Ashtekar singled out that was of particular interest to me was several pages later, and that is that in 1960, Arnowit, Desser, and Misner, ADM, as they are referred to, had constructed an exact relativistic, general relativistic, not special relativistic, model of elementary particles because they had found the solution for spherical cloud of charged dust. Okay? And it turns out that you can do this as Ashtekar lays it out here, and let me see if I can, wait a second. Am I pushing the right thing? Yes. Okay, this is a result you come to. In general relativity, of course, you can't treat the mass in Newtonian fashion, so when you get this equation here, you have to treat that as an equation, if you're solving for m, is quadratic in m. You apply the standard formula, you get this, and then as Ashtekar pointed out, if you let r go to 0, or r is actually epsilon in this article, what you find is that some of the terms go to 0, but you end up with a finite result. Okay, and you didn't have to renormalize anything, you didn't have to fudge, you didn't have to wave your hands or anything like that. You automatically get a finite result when you include both electromagnetism and gravity in this fashion. Okay, the problem, of course, is, as this is called, the ADM mass turns out to be the square root of the fine structure constant smaller than the Planck mass, okay, which is 10 to the minus fifth grams, which is obviously not the mass of any elementary particle with which we're familiar. Okay, this is an enlargement of the bottom of that slide. Okay, it has some positive features, but it has some drawbacks. It's too big. The simple bare mass of the ADM electron is positive, and what we know is that the bare mass should be negative, okay? Or at least if you take the standard model seriously, it should be negative. The question is what happens if you put in a negative bare mass in the ADM model. Okay, gravitation only enters as a local self-energy in the ADM model. That is to say, no account is taken of coupling to the distant matter in the universe. Okay, now for reasons other than anything having to do with this, back at the time that I was fiddling around with this, it had already occurred to me that you needed to take Mach's principle seriously if you were going to get very far in advanced propulsion. Okay, there's an interesting thing about the ADM mass, however. It differs from the electron mass by almost exactly the square of the speed of light. It's to within 10%, which tells you something. Well, it may be just a coincidence and it may be a red herring, but there may be something there. If you take Mach's principle seriously, what you discover is that the value of the total scalar gravitational potential is c squared, which suggests that maybe this has something to do with the ADM mass, okay? And that if you take into consideration Mach's principle, you might be able to get back a realistic value for the electron mass. Okay? The bare mass should be negative, as I said. And what does all of this lead to? Well, if you're interested in finding out the details, I'll be happy to either point you to papers that I've already published, or if you like, I'll be happy to send you a manuscript that's presently in progress that spells out all of this stuff about the ADM mass. What you end up with when you take a negative bare mass and you insist that the equivalence principle be correct, that is to say that when the gravitational mass of an object is negative, its inertial mass has to be negative too. Okay? This is, by the way, a mistake that is made by actually some rather surprising folks. Okay? When you drop a negative bare mass object, when you drop a negative mass object in the Earth's gravitational field, you will hear people who ought to know better say that it's repelled and therefore goes up. The fact of the matter is that it falls just like normal mass, because while the force is repulsive, the inertial reaction to the repulsive force is to make the thing accelerate downward. Okay? If that weren't so, the equivalence principle would be false, general relativity would be wrong, and we'd be all in deep trouble. Okay? Because it's the metric nature of general relativity that allows you to talk seriously about wormholes and stargates and stuff like that. Advanced propulsion wouldn't be nearly as much fun if general relativity were wrong. Okay, let me point out here that, oops, pushed the wrong button. Sorry, oops, that's the wrong direction. Here we are. Okay. This is the total gravitational potential due to the universe, has a value of c squared, up to some numerical factor of order unity. This is the potential due to the cloud of electrically charged dust. It has negative bare mass, so this is a negative potential. This is a positive potential. When you add those things together, they're both equal to about c squared. What you end up with is this thing dominating the denominator, and that gives you back the electron mass. Okay, up to factors of order unity to within 10% if you fudge all those order unity numbers the right way. Okay? If you could figure out how to suppress this, this would no longer be canceled in effect by an equal and opposite potential, and what you would end up with is this thing being of order unity, and you would end up with the ADM mass being exposed, the bare mass of the elementary particles. And if you work out the algebra for arithmetic for this, what you discover is that if you have a sphere 30 meters in diameter, about a meter thick of normal stuff, and you figure out how to suppress this thing here, this thing turns it into a Jupiter mass of negative rest mass matter. Okay? So in principle, if there's anything to this, and I emphasize if there's anything to this, in principle, you should be able to make Jupiter masses of negative rest mass matter to produce wormholes and warp drives and all the rest of that, okay, if this is right, okay? How do you do it? Well, by making phi sub u small or zero, okay? Can it be done? With low energy electromagnetic fields. How? That's where Mach's principle comes in. Okay? That, by the way, is Ernst Mach in his study, I believe it was around 1888 or thereabouts, in Vienna. Okay? What is Mach's principle? You push on something, it pushes back. Why? Well, people used to argue about this, but if you look at the physics of it, you can say the gravitational action of distant stuff out there. Okay? Now, as you've heard, there are many different versions of Mach's principle. Indeed, the subtlety of the distinctions in some cases becomes almost illusory and all that. And people used to fight about this quite vehemently at times. Okay? But this guy here, in his doctoral work with Paul Dirac back in the early 1950s, that's Dennis Sciama, who died about 5 years ago, okay, in a few lines showed in a vector theory of gravitation, which is of course only approximation to general relativity, but nonetheless, you know, at the time Sciama thought it wasn't general relativity. It's turned out that it is general relativity in disguise. Okay, it turns out that if you take the gravito-electric field to be the analog of the electric field in electrodynamics, and then you ask what A is, the vector part of the force potential for the gravitational field, A turns out to be the integral of matter currents over all space and all that. Sciama used a neat trick here so that you don't get involved in lengthy, tedious calculations involving lots of algebra. Okay. He said, hey, look, if you look at an object and it's being accelerated, it looks to that object as if the universe is rigidly being accelerated in the opposite direction. Okay. So you can take V out of the integral here, and all you have to do is integrate over the matter density. Okay. When you do the integration over the matter density to get A, what you find is that you get just the scalar gravitational potential. Okay. So the gravito-electric field ends up being minus the gradient of phi, minus phi over c squared times the time derivative of the velocity of the object. If the velocity is constant, that term is zero. Okay? If the velocity is not constant, that is to say if it's being accelerated, of course, then that term is not zero, and if the term in front of it, the factor in front of it, phi over c squared is equal to 1, it turns out to be the inertial reaction force. Okay? It's as simple as that. What this means is that in any theory of gravity where you have so-called critical cosmic matter density, okay, which is characterized by space being flat, okay, phi turns out to have that property. It turns out that inertial reaction forces in general relativity are provided by the gravitational action of distant matter, because since the W map results, we know that space is flat. Okay, it's as simple as that. Now, of course, there are scads and scads of people who don't care or don't pay attention and don't know this. Okay, but this isn't a matter of something that you can really argue about anymore, where 10 years ago it was. Okay, that's nice, but how does this help with the Jupiter mass of exotic matter? Okay. Well, we need to ask about local sources of the field. Okay. Part of advancing middle age is you become less concerned about covering your tracks and more concerned about making sure people get what you're trying to say, and hopefully that they will have interesting criticisms because you can learn from that. If you just wave your hands and all the rest of that and they don't get it, then of course no progress is made. Okay. Before I got interested in Mach's principle, well, not really, but before I got seriously interested in Mach's principle, I was interested in theories that coupled gravity and electromagnetism in ways other than the naive Einstein-Maxwell equations. Okay? One of those was a suggestion by Arthur Schuster back around the turn of the 20th century, which had been followed up by Patrick Blackett, the 1947 Nobel laureate in physics, for work on cosmic rays, that rotating neutral massive objects might generate magnetic fields, real magnetic fields, not gravitomagnetic fields, a real magnetic field. A fellow who was then a graduate student in Ontario, Canada, named George Luchak, who I believe ended up as a professor of electrical engineering at Princeton for most of his career, okay, sat down and wrote out a set of coupled field equations to go with Blackett's hypothesis, okay, published in the Canadian Journal of Physics, 1953. This is from his paper, okay. Those are the coupled field equations that give you back the Schuster-Blackett effect, okay. Luchak wasn't interested in the details of general relativity. So what he did was he wrote down his coupled field equations as the four-dimensional formalism being electrodynamics, Maxwellian electrodynamics, and then he used his fifth dimension to include a relativistically invariant version of Newtonian gravity. That's these three equations here. Okay. The one that's of interest here looks very, very much like this equation up here. Well, similar anyway. Oops, wrong direction. Okay. The standard equation, the standard Lorentz invariant equation for a propagating field, of course, is one where you have the divergence of the force plus 1 over c squared times the time derivative of the field and so on is equal to the sources. It's the D'Alembert of the field is equal to its sources. Okay, so if you look at this term here, that turns out to be the rate at which the field does work on its sources, Q. Turns out to be that. And in fact, there's a good reason for that, as you can discover by reading Wolfgang Rindler's outstanding little book on Introduction to Special Relativity. Okay? And you'll find in section 35 this little discussion here. Okay? For example, if two particles collide elastically, their rest masses during collision will vary. Okay? That might be when you're interested in them, and then he develops this formalism. Unfortunately, it was only laid out this clearly in the second edition, which was after I had struggled through all of this stuff myself, okay, and wasn't quite sure that it was right. It turns out that it is. Okay. What? 3 pages of algebra gets you from that. Aha, that's where the 3 pages of algebra. Okay. Basically what you do is you ask yourself the following question. If an inertial reaction force is indeed being generated by the gravitational field due to the distant matter in the universe, okay, what happens as you accelerate the object? You can just simply ask what are the local sources of the field. And if you take f, the 4-vector f here, as being divided by the mass of the object that's being accelerated as the field in question, then you could simply sit down and calculate using this expression for the 4 force what that has to be. 3 pages of algebra, okay, get you there. Okay, the D'Alembert of the field is equal to what we normally think of as the sources, plus a bunch of transient terms. Now, the thing that I want to emphasize for you here is that there is no hand waving involved. This is really, to be perfectly honest about it, undergraduate level physics. This isn't some esoteric thing like that. Okay, what that ends up with is the equation that York Dobbins showed you earlier this morning, and then pointed out that it makes some predictions, if treated in a fairly straightforward and naive way, that are dubious, to say the least. Okay? What you end up with is this equation, and notice that it has two parts. The linear term, which is the one that he was talking about, produces enormous effects. You can engineer situations where you can get really, in principle. In practice, this turns out to be a different matter. But in principle, you can produce very large effects with that term. Indeed, so large that if you can figure out how to do it right, you can make thrusters that you should be able to sell to NASA because you're not blowing any propellant out the tailpipe. You're gravitationally coupling directly to the rest of the universe, and so on and so forth. You have to put energy in to do this, but you don't have to worry about carrying along a lot of stuff that goes out the tailpipe. Okay, what I want to emphasize today, however, is this term. Oops, I keep pushing the wrong button. This term here, notice that it's smaller by a factor of c squared than this thing here, the coefficient of the power terms. P is the power, IV, for a capacitor or something like that. This, by the way, is not voltage, that's the volume. Notice that the first term is independent of the volume of whatever you're doing, but this one turns out to be a density. So you have to get high densities in order to make this term large. The really interesting thing about this term is that there's a minus sign in front of it, and everything else is squared or positive. Okay, that means that term is always negative. Okay, and as a result, we call it the wormhole term, me and my group of virtual over-the-shoulder lookers. Okay? It turns out you can do a crude numerical integration, and you discover that with reasonable assumptions that you can transiently, by cycling the first term here, so that rho 0, which occurs in the denominator of these coefficients, can be driven to 0, and when the coefficient is 0 in the denominator, the coefficient becomes infinite, of course, formally. That means that this term here, normally a factor of c squared smaller than the leading term, dominates the equation. And in principle, you ought to be able, if there's anything to all of this, okay? In principle, you ought to be able to make idiotic amounts of negative rest mass matter, that is to say your Jupiter masses, in reasonable sized structures, and since this is a process which is induced in situ, you don't have to worry about collecting a bunch of stuff and trying to compact it down into your 30-meter in diameter sphere. It's already there, because you and me and everything else in the world has this lurking inside of our elementary particles. The negative rest mass is already there, okay? Okay, now, the question is there anything to this at all? And the answer to that question is, if it doesn't get supported by experiments, convincing experiments, the answer is nobody's going to pay any attention to it. They may not pay any attention to it anyway, but that's their problem, not yours. My problem is to see if there's anything to this at all, and indeed, following this is from an earlier presentation where I was talking about small steps and all that, but I'll show it to you anyway. Okay. What you do is you try and induce a fluctuation and push on the object when you're making the thing a little bit more massive and pull back on it when it's a little bit less massive. This is the linear analog of York's wheel. Okay, fair enough? Fair enough. Okay. This is Nembo Boldrini's animation for a presentation that he did that I got from him, okay? It's really much cleverer than anything I could have come up with, okay? Is there any evidence at all that suggests that this might be right? Okay, I'm going to tell you a little bit, and how am I doing on time? 5 5 minutes? Okay. 5 minutes quickly. Okay. The experiment that I'm working on now implements an idea of a former graduate student of mine, which is basically to take some active material which are going to drive with an alternating voltage which will produce a sort of internal energy fluctuations that should produce mass fluctuations when they coincide with an acceleration. A mistake that we made, including myself, for a long time was to assume that you could just simply apply an AC voltage to a capacitor and you should induce mass fluctuation. If there isn't any bulk acceleration present, there's no mass fluctuation. And the reason why is because when you construct the equation to which you get the transient terms from, you assume that you're bulk accelerating the thing that has the energy change taking place. Okay, the other ends of these are also piezoelectric actuators in this case. Their polarities are set up this way, so when you apply a voltage to them, one of them contracts, the other expands. It basically shuttles the material in between, back and forth. Then all you do is apply, there's one of these devices sitting between clamping blocks here, aluminum clamping blocks, on the end of a very, very sensitive torsion balance, which I'll get to in a moment. What you do is you apply a voltage to the capacitated material in between, and you apply another voltage which has two components. One at the frequency of the applied voltage to the so-called capacitor up here, what I'm calling the capacitor, to accelerate it to produce your so-called bulk acceleration, and a second double frequency signal, because the mass fluctuation allegedly occurs at the power frequency of what you're doing, and that, of course, is the product of a couplet sine and a cosine or whatever. That gives you a double frequency signal. And then you have to provide for phase shifting and locking and stuff like that. Okay, bunch of technical details. This is more or less what the device looks like. Okay, the reason why these are C-flex flexural bearings supporting this torsion balance arm, so on, that was because of Nembo Baldrini's use of Martin Tamar's thrust balance, which looks like this, okay, similar to this at any rate. Okay, there's a counterweight over here to counterweight the device. There are some calibration coils here so that you can calibrate the system. The really important part of this device is right here. Coaxial with the flexural bearings here, you have a set of gallon stand contacts because you're putting a fair amount of power on the order of 10 or 15 or 20 watts through these contacts. And if you're trying to measure things on the order of 10 to 100 nanonewtons, you've got to be extremely careful about stuff like this because it's real easy to mask what you're looking for with spurious stuff. Okay, this is a close-up of the gallon stand contacts. This is, I especially like, yes, 1 minute. This picture of it, okay, real quickly. Results from January. The way in which you do this is you turn the whole thing on. That's what happens. Oops, wait a second, pushing the wrong button. That's what happens here. That offset is just an electrical offset. Basically what you do when you turn on the power is you shift the ground level in the system because of ground return currents and all that. Okay, the red trace here is an accelerometer in the middle of the stack, which tells you what's going on in the stack. The blue trace is the position sensor, an optical position sensor, so that it doesn't get electromagnetic pickup and so forth. And as you can see, when you turn it on, the thing does this. When you flip a switch and invert the phase of the actuator signal, what happens is the thrust changes. And that should not happen if there is no effect present. Okay? And then when you flip it back, it goes back and so on. Okay? And for a while, late in January and early in February, time to shut up, huh? Okay, 2 seconds? Okay. Quickly as possible. These are the sort of traces you're getting. What I'm showing you is reality. What happens in reality is you can see things are beginning to grade a little bit. The height of this thing here isn't the same as the height of this thing here, which means that you have thermal evolution in this region here where the thing is on. There's major thermal evolution, okay? And this is catastrophic thermal evolution, and after this happened, the device never worked that way again, okay, which is not good news from the point of view of continuing to fiddle around with it, but it is good news from one point of view. It tells you immediately that a whole bunch of spurious things that you might have to investigate are not the cause of the signal you're looking at. Okay. After a few months of fooling around, new device, there it is wired, there it is on the end of the balance, there's some neat stuff, more stuff, and that's the trace that was to be the beginning of a series of traces that I would have told you about in great detail here today instead of wormholes and negative mass matter. The power amplifier died. Right there. That's a transient of the power amplifier dying, at which point I decided these are signal generators. Okay. Okay. And there is no time for questions, I assume?
Yes, there are a few minutes for questions.
Okay.
And I will recuse myself from asking anything because Dr. Woodward and I have had a sort of indirect correspondence on a number of these topics. We could probably go on arguing for hours.
Yes, if inertia is viewed as a reaction from the rest of the universe, then how does that happen instantaneously for any kind of acceleration?
That's why John Kramer and I are really good friends. It's a radiation reaction interaction, presumably, which involves a Wheeler-Feynman advanced retarded interaction. Yes, that is the obvious question to ask if you say that. One way of answering it, which there is another way of getting it instantaneously, and I should tell you to be full disclosure, and that's to use the constraint equations, which are elliptic instead of hyperbolic, and then you have a field here